Hello everyone. In this video, we are going to see how we can do keyword extraction using sentence transformers. Let's say, for example, we have the movie plot of Interstellar, and from the movie plot, how can we identify important keywords and extract them? That's what we are going to see today, which is extracting keywords or key phrases from any context. A big shout out to Martin who built the keyword library, and a lot of things that we are going to discuss today are based on the keyword library. So if you think about keyword extraction algorithms, there are a lot of algorithms, let's say TF-IDF, where you can extract the top n-grams that have the highest TF-IDF scores in a given document, and those will be the keywords for the document. But the problem is that to extract keywords using TF-IDF, you need to have a corpus of data to calculate the IDF scores and then extract TF-IDF, etc. And there are also unsupervised algorithms like topic rank, multipartite rank, etc. that are graph based. But if you want to go beyond the graph based algorithms and also look into some semantic similarity to extract diversity in the top n keywords, etc. So this algorithm of extracting keywords using sentence transformers works perfectly. We are just going to see that. So the step one would be extracting all noun phrases or verb phrases from the text. So these can serve as candidate key phrases or keywords from which we are going to filter out the top ones. So in order to extract noun phrases or verb phrases, you can use any library like Spacy, etc. and you can just extract noun phrases or verb phrases from the text. And step two would be converting the whole text into a vector. So the whole text or document, or in our case the movie plot, you can take the whole document and use the sentence transformers library SBIRD and convert this into a single vector of, let's say, 384 dimensions or 768 dimensions, etc. The dimensions depend on the exact sentence transformer model that you choose from SBIRD. But nevertheless, let's assume that we create a vector of 384 dimensions from this. So in step 2, this whole movie plot is converted into a single vector of 384 dimensions. Let's call this the document vector. And here comes the interesting part. We have extracted all the noun phrases and verb phrases from the document. So for example, let's say in our Interstellar movie plot, we have about 120 noun phrases or verb phrases. Now take each of the noun phrase or verb phrase and convert that into a fixed vector of, again, size 384 dimensions, etc. using the same sentence transformer model that you used in step 2 to create the document vector. So now each of this 120 key phrases or keywords, each of them is converted into a single vector of 384 dimensions, as you can see here. Let's call these as phrase vectors. So there are about 120 phrase vectors in our case. Now we arrive to step 4, which is the most interesting part of this, which is we are going to take the cosine similarity of the phrase vector and the whole document vector, and we are going to do that for all the phrases that we have. So at the end of the day, we are going to get cosine similarity score of each phrase vector with the document vector. So for example, 0.188 is the cosine similarity score of crop blights and the whole vector that we obtain from this. Similarly, we get the 364 dimensional vector for dust storms and take the cosine similarity of this whole document vector, that is also 364 dimensions or 380 dimensions. the same dimensions essentially, and we are going to get 0.435 etc. As I mentioned, we get cosine similarity of each phrase vector with the document vector and extract the scores in step 4. And step 5 is actually sorting all the keywords in their decreasing order of cosine similarity, and we are going to get this. So at the end of the day, we get this, which is Cooper ships, former NASA pilot, Murph's dust covered bedroom floor, etc. And you can see these are the cosine similarities when compared to the whole document vector. So essentially we are just sorting out these cosine similarity scores that we extracted in the decreasing order, and also finding the corresponding key phrases or keywords. Now the beauty is that we have created a very simple algorithm, which is out of all the noun phrases or verb phrases that we extracted, we easily ordered them in the decreasing order of cosine similarity, and we already got our, let's say, top 10 keywords or key phrases for the document, etc. So this already stands for key phrases or keywords of the document, because these keywords or key phrases are the most similar when you compare to the whole document vector. But here's one big problem. We have solved our key phrase extraction by simply sorting out the most similar keywords compared to the whole document. But we do see that there are a lot of redundancies here, because probably from Cooper and Cooper ship we just want to keep one keyword, and from Murph's dust covered bedroom floor, the dust patterns, Murph's old bedroom, Murph's room, out of these probably we just want to keep only one, because there are almost 3 references to Murph's bedroom or room, and maybe we just want to keep only one from that. So the biggest problem is that we have identified which key phrases contribute the most to the document vector and are prime to the document vector, but we do have a lot of redundancy here. How do we explore some diversity here? Can we get the top 20 key phrases and then from that pick the top 5 key phrases that are the most diverse? Can we do that? That's what we are going to see in the next steps. So how do we add diversity? For example, I've taken a bigger selection of sorted keywords from our interstellar movie plot, and as you can see, I've color coded them, where perhaps you have about 20 or 25 keywords, and from this, if someone says extract the top 3 key phrases from the document, perhaps you're going to only pick one from each color. From Cooper and Cooper ship, perhaps you just want to keep one word, one key phrase, let's say Cooper, and then you have Murph's bedroom floor, Murph's old bedroom, Murph's room, you want to keep only one from there. And then you have let's say the younger Murph, an elderly Murph, the adult Murph, you might want to keep only one. Then you have the dust patterns, dust storms, a dust storm. From this you might want to only keep one. As you can see, I've color coded keywords that are close to each other, perhaps that you want to group them and keep only one keyword from there. The interesting thing is that there are about 2 algorithms at least that we are going to see. One is called as max sum similarity, and the second thing is maximum marginal relevance, MMR. We are going to get an understanding of how these two work. Let's start with max sum similarity. So let's say we have these 20 keywords, for example, or 15 keywords, as you can see here. And if our goal is to extract the top 3 key phrases from this, let's see how we are going to approach that. So just to reiterate, perhaps our document will have 120 noun phrases or verb phrases, out of which we sorted all the noun phrases or verb phrases in the decreasing order of similarity, and then we pick, let's say, top 20 key phrases or noun phrases from the sorted list to consider as candidates. Now we have encountered one problem, which is there is a lot of redundancy there, and what we want to do from that is smartly pick only 3 key phrases from the top 20 while preserving the diversity. So let's see how we can pick top 3 key phrases from this. So max sum similarity is not too complex. So create all combinations of 3 key phrases from this 20 key phrases that you can get. I mean, in mathematical sense, you will find all permutations and combinations of 3 key phrases that are possible from these 20 key phrases. And let's say one such combination is Dustrom's, Coopership and Professor John Brand. Remember that since we are going to just calculate max sum similarity, we can see that within these 3 words we can just interchange their order, and the cosine similarity that we are going to calculate doesn't change. So basically pick 3 key phrases from these 20 key phrases without replacements. Let's see how we can calculate some similarity between these key phrases. It's pretty simple. So cosine similarity of, let's say, key phrase 1 and key phrase 2 and key phrase 3 is essentially taking the cosine similarity of all the combinations that are present, K1, K2, K1, K3 and K2, K3. Technically 9 combinations are possible, but we don't want to do K1 with K1 and K2 with K2, so those are removed. And you can do K2 with K1, but that's just going to be again cosine similarity of K1 and K2 itself. So either you can just take 2 times this thing, or if you want to ignore the number 2, you can just take the cosine similarity of K1, K2, K3 as the sum of these 3 combinations. And the beauty is that you will calculate this cosine similarity of K1, K2, K3 for all the permutations and combinations of 3 key phrases that you can pick from the total n, let's say 20 key phrases. And what we are going to do is find the triplet that has the least cosine similarity, and those 3 will be the top 3 key phrases from this document. And why are we saying that is simply we want to pick 3 key phrases with the maximum diversity. And when does maximum diversity occur? If there is least similarity among those 3 key phrases. So that's why we are calculating the similarity among those 3 key phrases with this formula. And if we pick the combination, the triplet combination that has the least cosine similarity, then essentially we have picked top 3 key phrases that are the maximum, that have the maximum diversity from top n sorted key phrases. So that's essentially max sum similarity, and this number can differ. You can keep this as top 5 key phrases, and also you can do a hard cutoff at 20 or 30, etc. But just remember that since this is a very computationally intensive algorithm, perhaps keeping these numbers low will make it faster. Otherwise the algorithm becomes slower as you increase any of these parameters. And the next interesting algorithm is called as maximum marginal relevance, MMR. Again, let's choose the goal that we have to extract top 3 key phrases from this document, and we have again cut off at, let's say, 20 key phrases, and from those 20 key phrases we want to extract top 3 key phrases with the maximum diversity again. So maximum marginal relevance is given by this formula. Don't be intimidated with this formula. I'm going to intuitively explain it to you, but just remember that here Q stands for document vector, that is the whole movie plot, and D stands for key phrase vector. And we are going to see what this lambda is. When you keep lambda as 0, you get the maximum diversity, and when you keep lambda as 1, you get minimum diversity when compared to the original document. So let's go through this. So essentially what's happening here is that we have the whole document vector, and we have these keywords which are sorted by their similarity to the whole document vector. But in order to pick, let's say, top 3 key phrases, there are 2 parameters to consider. The first parameter is, among these top 3 key phrases, how similar is each key phrase when compared to the original document vector. And the second parameter is the intra key phrase similarity, that is, within these 3 key phrases, how much do they differ with among themselves. So lambda is exactly that parameter which controls how much you want these key phrases to be similar to the original vector, that is the full document vector, as well as preserving the intra key phrase similarity, that is maximizing the similarity difference between these top 3 key phrases. Now I'm just saying 3, but you can assume that this could be another parameter n. It could be 5, 10, whatever it is. So precisely speaking, this similarity of D, Q, this is the first parameter which considers how close a given keyword is with respect to the document. And this is the second parameter, calculating the intra key phrase similarity and maximizing that part. So you can vary lambda between 0 and 1 and get that fine level of control, how much you want the key phrases to differ from each other and how much you want them to be similar to the original document. In order to understand this equation, let's first assume that lambda is equal to 1. So when lambda is equal to 1, this becomes 1 and this whole thing becomes 0. MMR is an iterative algorithm. That is, if you are extracting, let's say, top n key phrases, here n could be 3. Each time when MMR is run in a loop, every time one key phrase is extracted. And let's take lambda is equal to 1 to understand this. Basically, you remove the whole thing here. And when lambda is equal to 1, only this thing is remaining. And when MMR first runs, what's going to happen is that we get the similarity of every key phrase with the document. So we get the similarity of Cooper with the document and Cooper ship with the document, former NASA pilot with the document, etc. And in the first round, in the first loop, we are going to extract the word that has maximum similarity. That's going to be Cooper anyways, since we have already sorted this. But MMR works even on unsorted list. So you can give your complete 120 key phrase vector list. You don't need to sort them at all. You can just give them directly and MMR will extract. As you can see, if lambda is equal to 1, what MMR is going to do is just create this sorted list. That's it. Why? Because in the first round, it will find one word among these 120 words that has the highest similarity, which is Cooper. Then that's added to the top n key phrases. Now for the second key phrase, among the 120 keywords, we already removed Copper. So among 119 keywords at random, it will try to calculate which has the highest cosine similarity with the document. That's going to be Cooper ship anyways. So it's going to extract that. Then third will be formal NASA pilot. So at the end of the day, if lambda is equal to 1, basically this MMR algorithm will just come back to what we have previously created, which is a decreasing order of sorted list of keywords. So when lambda is equal to 1, there is no diversity, because you can see that there is no diversity in our purely sorted list based on just cosine similarity from highest to lowest. Now in order to understand this equation, let's just think of the other scenario, which is lambda is equal to 0, then this whole term will be gone and we just have -1 max similarity of di dj. And the beautiful thing to remember is that when lambda is equal to 0, all we are doing is compare these, let's say 120 key phrases among themselves to extract the maximum diversity. There is no comparison with the original document at all. Why? Because when lambda is equal to 1, this q document vector, this whole term is gone. It is completely 0 and we just have -1 and lambda is equal to 0 here. So minus max similarity between di dj, which is intra key phrase similarity itself. Don't worry, I'm going to explain what this is. But just remember that when lambda is equal to 0, there is no comparison with the document at all. It's completely gone. We are just comparing key phrases among themselves because we have corresponding vector of each key phrase. So we are essentially comparing the vectors among themselves. And what's happening is when lambda is equal to 0, first we initialize with the most similar keyword, because since we are doing intra similarity, we need at least one keyword to be present in the top n keyword list that we are creating. So first Cooper or the most similar keyword is added. So it's initialized with that. But in order to truly understand how this loop works, let's take this scenario where you are extracting 3 keywords from this list and you already have 2 keywords, that is Cooper and dust patterns. And when lambda is equal to 0, everything is gone. So let's see how the third keyword will be extracted. Once you understand that part, it will be very clear for you. So simply put, again MMR extracts keywords in a loop. So assume that in the top 2 loops you already extracted Cooper and dust patterns. Now how is MMR algorithm going to extract the third keyword when lambda is equal to 0? Simply what's going to happen is that out of the 120 keywords, we already have 2 keywords extracted and kept in the top k keywords list, top n keywords list. Now out of the remaining 118, our goal is to extract the next keyword. So what happens is that we have 2 on this side and we have 118 on this side. We are going to compare every keyword on the unselected list with the selected list. So that's exactly that's happening in this equation here, sim di dj, where dj belongs to s. So here dj means the subset that is already selected. So we are going to calculate the score for every keyword, which is simply you take, let's say the keyword copper ship, you are going to get its vector and you are going to get the maximum cosine similarity when compared to each of the words that are already present in the keyword list. So simply score of copper ship is max of cosine similarity of Cooper ship with Cooper, and then cosine similarity of Cooper ship with the dust pattern. Simply put, you will get the max cosine similarity of this word compared to both of these things. Similarly, you will do the same for former NASA pilot, Murph's dust covered bedroom, and for rest of the remaining 118 words you will do the same, which is extract the score with this formula. It's nothing complex, just getting the maximum cosine similarity that you encounter when compared to the subset that is already present. And next, the beauty is to choose among all the scores of 118 words, you will find the word that has the least cosine similarity, that is least of max cosine similarities that are extracted. Simply put, the most diverse third keyword is the one that has the least score. So in this formula, how it works out is that now you extracted the max score, and if you have lambda is equal to 0, it becomes negative. So since you are extracting max of negative scores, it's almost like just min of all the positive scores. So at the end of the day, you get the scores for each word, which is based on this calculation. and you will find the word that has the least score when compared to these words, and you will add that as the third keyword. And pretty much the same thing is repeated for the fourth keyword. Now instead of comparing with just 2 words, you will compare 117 keywords with the 3 keywords that are already present and extract the max similarity score for each keyword and find whichever has the least similarity score, add it as the fourth keyword. And the pattern repeats itself until you extract top n keywords. That's basically maximum marginal relevance, MMR. And the beauty is that we understood how it works in scenarios when lambda is equal to 1 and lambda is equal to 0. But simply extending that, if you just want to find the perfect balance of being similar to the original document as well as being diverse among themselves, you can just play with any other parameter. Let's say lambda is equal to 0.5. Then in those cases, the algorithm works in similar pattern, but here when lambda is equal to 0.5, you will find a good balance between the keywords being diverse among themselves as well as being close to the original document vector. And just to recap everything again, in the first step we extract all the potential noun phrases or verb phrases, and then we convert the whole context into a vector. Then we convert each of the noun phrase or verb phrase into a vector. Then we calculate cosine similarity of each potential key phrase with the whole document vector. Now you sort them by the similarity of their scores from highest to lowest. So essentially these are the key phrases corresponding to the given document. But there are a few problems, that there is quite a lot of redundancy. So in order to overcome the redundancy, you have 2 diversity algorithms. The first one is max sum similarity, where you'll pick 3 key phrases with all permutations and combinations possible from a given fixed set of keywords, and you'll see which triplet of key phrases has the least cosine similarity score when the vectors of theirs are compared with each other. Now I'm just mentioning 3, but that could be any other value like 5 or 6, etc. Then there is maximum marginal relevance, which strikes the perfect balance between the key phrase being close to the original document vector as well as preserving the intra key phrase diversity. You can control that balance with lambda, which varies from 1 to 0. 1 means there is absolutely no diversity, and 0 means you have the maximum diversity. Thanks for watching.